Now the second one is now big omega. Big omega it is used to find the lower bound of any algorithm. Like for in this example, let's say we are plotting the time complexity with the number of input. If we plot any the function graph of any particular algorithm, which goes like this, it is defined as f of n here, and we get the graph of time complexity with respect to number of inputs, and it comes to be like this. So the lower bound, we have to define a function called c of g of n, such that the lower bound is going so it is going to be lower than the time complexity of this function f of n in all the for all the input n, given that the function of f of n should be greater than or equal to c of g of n. C is again a constant and n is the number of input. Now here n should be at any given n0. Now at any given n0, and this equation will hold for any n which is greater than n0, and any constant 0, any constant which is greater than 0, and not greater than or equal to 1. And not is nothing but a number of input. For 0 we are not going to calculate any value, so it's obvious that we have to have more than one input. So we can actually define this thing with an example. Now let us see an example where we can find the values for the lower bound in terms of big omega. Suppose the function of f of n is equal to 3n plus 2, and g of n to be n. Now for a function of n to be equal to big omega of c of g o n, then in such conditions we have in this condition we have to find the function f of n to be greater than or equal to c of g of n. I'm sorry, it should be g of n only. Now let's place the values here. 3n plus 2 is greater than n. So for this value will be always going to be true for the lower bound of n, because we know that this value is going to be greater than n for any c, even if the c value of c is 1. Now we have to check whether this condition will be hold for n equal to n square as well. Now we have to check whether this value will be satisfied for any values of g of n for n square. Now if we pull this value here, n square, we know there is no such value of c which can hold this condition for any given n0 which is greater than or equal to 1. Now we will not be able to find any value which is going to of n which is going to hold this value n and c. So we can say that any value of n, any function of n or f of n can be the big omega of any value which is n or less than n. It can be log of n or log of base 2 of n, so on and so forth. Now this means that any value which is of n which is less than n can be lower bounded with big omega, but again we have to find the tightest bound of for this condition. So in that case we are going to use n. Similarly, like in big O we have used n, or in case of big O we have used n square, n cube, which can be used, but we have used the tightest bond. Here we are going to use the tightest bond as well.